Now we're going to examine the topic of transformations, like our point transformations, in the context of Hamiltonians. Let's take an example. Let's start with the Hamiltonian for a particle falling under gravity, just in one dimension, so we'll just have z and pz. Okay? And so it's going to be of the form of kinetic energy plus potential energy, p squared on 2m, plus the potential, which is just mgz. And this would lead us to the equations of motion. Remember that pz dot is just going to be minus dh dz, and z dot is going to be dh dpz, which means that the z dot is just going to be pz on m, and our pz dot is just going to be minus mg, as before. Now supposing we're going to make a transformation. We're going to go to capital Z and capital P, and these are going to be almost the same as the old Z and P. We're just going to scale the Z, alpha little z, and P is going to be exactly the same. So that would imply that if we were to just make that transformation, that our new Hamiltonian of big Z and big P would just be the same kinetic energy term, big P squared on 2m, except this time our Z will be scaled, mg big Z on alpha by our scaling factor. So that's a straightforward change of variables, but Hamilton's equations still apply. Well, let's check. And therefore, if I was to transform back again, what I would end up with, little pz, the same as this pz, is my, what? I shouldn't have an alpha there. My little pz was supposed to be just mg, so that's not right. And then if I come over here, my big P on m, my little z dot, which is going to be z on alpha, is going to be big P on alpha m. So the main problem with this is that it's wrong. Where did it go wrong? It went wrong precisely because it turns out that just because you make this point transformation on your coordinates, you don't get to change the Hamiltonian like that. Why don't you get to change the Hamiltonian like that? The momentum is defined in terms of the derivative of the Lagrangian with respect to our coordinate. So the big P, when you change your definition of Z, has to change. Right? So you don't get to make a completely arbitrary transformation on these two coordinates. When you change Z, you must change P. So this is the long and correct way of doing this problem. If you want to make this transformation, you do that for the Lagrangian instead. So the Lagrangian, remember, which would have been kinetic energy minus potential energy, so it was a half m little z dot squared minus mgz. If we make this transformation, then we get that factor of alpha in the kinetic energy. And then, and this is the critical bit, this Lagrangian is what defines our capital P momentum. So our capital P momentum, remember, is defined as the derivative of the Lagrangian with respect to z dot, which is just m capital Z dot on alpha squared. And so now when we calculate our Hamiltonian in terms of our capital Z and capital P, it's defined as our capital Z dot and our P minus our Lagrangian. And the fact that we have this version of capital P is going to change things. We're going to end up with a half m capital Z dot squared on alpha squared plus mg Z on alpha, and this is going to give us, which you'll note is completely different from this, because now we have that alpha there, but now we have an alpha squared up there, which will fix our problems here. So what we've learned is that there are restrictions to the kind of transformations that lead you to Hamilton's equations of motion. So you can't just take your equations of motion and do point transformations to them. There are restrictions. In fact, Hamiltonians aren't as easy to transform as Lagrangians, but you can transform them in much more dramatic ways. You can, in fact, transform a Hamiltonian all the way until it's trivial. Like, for example, you can make the Hamiltonian equal to 0 if you push it hard enough, which of course makes solving the Hamiltonian or the system trivial because then neither of the coordinates will evolve. And if you're going to get to that, then what you've done is you've effectively found the coordinate system that is the solution to your problem. And so you end up solving an integral rather than solving differential equations. And this is actually a method of doing classical mechanics that we're not going to go into. The keywords there are the Hamilton-Jacobi equations. It's just a method of finding all kinds of transformations that transform deliberately your Hamiltonian into a trivial one. And then you can do some more detailed analysis of the behavior of complicated systems.